Okay, let's move forward to the next thing we need in modeling, especially energy and mass transfer. We looked at diffusion. The next one is advection, and then combining advection and diffusion to produce some governing equations that begin to lead us towards modeling the climate, right? So advection is maybe something you've heard of, where things are carried by the flow. So imagine there is a heater and it's putting out energy. Air gets heated and air then moves and it takes the heat with it. So as opposed to the molecular diffusion, here things are being advected. So we'll start again with the one-dimensional situation where there is a cross-section A and distance delta x over which we are considering some concentration or amount that is present. So we move it in time delta t, we move it by delta x, which will be the speed at which things move in this fluid, or speed at which fluid is moving, u times delta t. So we carry c by distance delta x across a. So a delta t is the change in time. So the flux then becomes A is the cross section times delta x, that gives us volume, times the concentration C, the amount moved, and it has moved A delta t. So we end up with cancelling A delta x over delta t times C, and delta x delta t as you go to delta t and delta x go to 0 is of course the velocity of the fluid. So that gives us the term uc. It's in a very simplistic way of simplified way of deriving advection by a fluid moving at speed u, some concentration of the material c. So examples of advective fluxes of density denotes mass, and some particle or could be salt. So we looked at diffusion before, exact same thing here. Flux of mass would be u times rho, where we put a vector sign on top because we'll obviously quickly move to three-dimensional here from one-dimensional derivation. So heat is u times density rho times C, heat capacity C times temperature. So that's rho Ct is the heat contained in unit mass, and flux that moves across an interface is U times rho Ct. Salt is of course U times rho S, density of salt, and the y momentum equation is u times rho uy, where uy is du dy, the derivative of u in the y direction. This will become clearer as we come to the full momentum equation. It's just introduced here, but I think you have a sense already. So let's now move to the advection diffusion equation and continuity equation. Now let's move a volume delta V, which we will look at here. So we have delta x, delta y, and delta z. This is typically how most of the textbooks start the derivation, whereas Tom is starting with one-dimensional stuff. So you have fx here and fx plus delta x here, the flux. Similarly, you can have fy in this direction. So fy and fy plus delta y, and in the z direction you would have fz and fz plus delta z. That's typically how we would do it. So let's say we're still doing x direction, so d dt of c delta v, where delta v is now the volume, delta x, delta y, delta z. So fx times a, the interface area in the x direction, minus fx plus x, fx plus delta x times a. So what's coming in and what's going out is what is the net inside. And then there is diffusion happening as well. So we introduce a new vector operation here. The gradient dotted with another vector, diffusivity or diffusion coefficient times gradient of C. Remember, we wrote this part before when we did diffusion. Plus P, we have introduced a source and sink, so the net source of the material C could be salt, could be water or fluid. That's P. So here the divergence is an operator that basically takes two vectors and produces a projection which is scalar. So gradient is of course what we saw before, d dx, d dy, d dz, I, j, k in three directions. It is dotted with ux, uy, uz, which is again I, j, k. So it just gives you dux dx plus du y dy plus duz dz. Where now we have to be careful. So here this is u in the x direction, u in the y direction, and u in the z direction. So u vector is a three-dimensional vector. Okay, one could interpret I don't want to go back too far. One could interpret here this as u derivative of u in the y direction, but actually what Tom means here is the velocity in the y direction. Okay, so I hope I didn't confuse you there. So let's divide by delta v and write it as dc dt, which is what we are looking at. We're looking for time rate of change of C, like mass or salt, for example, and we combine the diffusion advection equation, write it as flux at x plus delta x, which is ux plus delta x times cx plus delta x, minus ux cx, which is the flux at x, divided by delta x in the x direction, and diffusion is d times dc dx in the x direction at x plus delta x, minus d times dc dx at x, as we saw before, depends on the gradient. Diffusion is always dependent on the gradient in a space. So delta x divided by delta x again, plus p. So this is what the equation gives, looking at this unit volume again. So I'm calling it unit, but it's delta x, delta y, delta z, and of course we are looking for derivatives, so we let delta x, delta y, and delta z tend to 0 to get continuous derivatives. So dc dt is minus duc dx plus d dx of d dc dx plus p. Okay, so obviously you can see you can move this term to here, and then probably some of you can begin to recognize the so-called total derivative, Lagrangian derivative, material derivative, and so on. So that's what happens when you move with the particle as opposed to sitting at one place and looking at material going through. But let me not introduce that quite yet. Making it three-dimensional, dc dt is then minus divergence of u times c plus divergence of the diffusion d grad c plus p. So this is obviously a Laplacian operator. So remembering that divergence of u gives us dux dy, dui dy, duz dz. You can do the same here. You have dc dx, dc dy, dc z here. When you do the divergence, you will get d squared c dx squared plus d squared c dy squared and d squared c dz squared or dz squared, plus the net source minus sink term here. We can quickly move that to density, so we can just replace c by density. And there is no diffusion of density, so we can just write it as d rho dt equals minus divergence of u times rho. For the ocean, rho is nearly constant. we considered incompressible, which cannot be done for the atmosphere, for example. But obviously it's a function of salinity, but if we assume it's constant, then you end up basically with d rho dt equals 0, because rho is constant, doesn't change in time. Then the divergence term just becomes du dx plus du dy plus, sorry, d rho dx plus d rho dy plus d rho dz equal to 0. So we can say an incompressible fluid is non-divergent. This tends to have all kinds of consequences when we come to it. So we will see what we mean as we move towards actual climate modeling. So this is the diffusion, advection, and advection diffusion with a source term. Okay, so we'll come and look at other processes of transferring mass and energy. Okay.